Okay, so if you watched my last screencast, then it's no secret that I'm a big fan of nuclear power, in that I feel like it is a proven technology that has the scale capacity to get us out of global warming and to essentially be a renewable energy source. Maybe not quite, but I'm going to explain to you in this presentation how it can move towards being a renewable energy source, just like solar or wind energy, except that the technology is here and it's already scalable to the levels we need to run our society. So let's just take a look at this. So I don't know if you remember from chemistry, the term isotope just refers to the amount of neutrons present in a particular element's nucleus. So you can have uranium, but you have different isotopes of uranium. So different, all uranium has 92 protons, but you could have different numbers of neutrons giving it different weights. So really, the word isotope just means atomic weight or atomic mass. Okay, so what happens though is uh, isotopes can, when they're unstable, they give off three different types of radiation, which is why you get this radiation symbol that we're all familiar with. This represents a nucleus giving off three different types of radiation, and I'm going to go through each type and explain why it would be given off. So alpha particles are the heaviest of the particles. They're essentially a helium nucleus. In fact, all the helium that you've ever played with in a balloon or inhaled, to talk like Donald Duck, all helium that you've ever encountered started off inside the Earth as an alpha particle being ejected from a heavy unstable isotope, basically anything polonium on up, 84 protons and more. And then it basically slowed down, acquired some electrons, and just became a helium atom, got trapped in an oil well, and then got separated through fractional distillation and put into your toy balloon. The point is this: an alpha particle is given off by large nuclei, and it's a heavy particle. All right. Now, beta particles are essentially high speed electrons, and they're given off also by heavy isotopes, but they're mostly given off by isotopes that have too many neutrons. So if there's too many neutrons, the neutrons become unstable, and the way they acquire stability is by ejecting an electron and then decaying into a proton. So the bottom line is, and this is going to be important with nuclear fission, that if there's too many neutrons, you are going to get beta particles emitted. Now, it turns out that whether an isotope gives off alpha particles or beta particles, often after it's done that, the arrangement, the configuration of the protons and neutrons is such that there's a diminishment in the nuclear potential energy, and since energy has to be conserved, the way it gets rid of the energy is it gives off gamma rays. So alpha and beta are particles; they have mass, but there's also just pure energy, which is given off by these gamma rays. And so it's just a way of reducing the overall potential energy present in the nucleus. So we all have grown up rightfully learning to be afraid of radiation. We want to reduce our exposure. What you may not realize is you get exposed to radiation every minute of your life, even when you were in utero, because radiation is just part of the natural world. It comes to us from outer space. There's gamma rays flying from outer space. There's neutrons flying from outer space. There's radioactive isotopes present naturally on Earth, even if humans had done nothing. So there's always this radiation, right? And the thing about radiation is, if you get dosed with a large amount of it, like you could get at a nuclear reactor or a nuclear weapon, uh, in that case, you can have what we call an acute exposure. You get exposed to so much that so many cells die all at once, especially the cells that have to reproduce real quickly, like the ones in your digestive system. You basically die from organ system failure. All right, but that's unusual. That takes large exposures. The more concerning thing is that we're all worried about is, well, we know that it can cause cancer, and cancer is primarily caused by mutations of our DNA. And as you go through life, you acquire these mutations in your cells, and if you get the unfortunate combination of these mutations, it leads to cancer. And so, exposure to radiation can lead to increased risk of cancer. Now, the thing is, alpha and beta particles, these particles, they don't penetrate into you. So if you have an external source of them, it'll hit your skin, but it won't penetrate below that. Okay, so generally speaking, these alpha and beta emitting particle emitters are a problem if they get ingested. like cobalt 60 is something that's produced by fission, and if we get that into our bodies, it can basically take the place of calcium in our bones and continually expose us to alpha particles, and that gives us cancer over time. Now, gamma rays are different. Gamma rays can travel like they have no mass, so they're not blocked by anything. They don't have an electric charge, so they can just fly through concrete. They can go like through a kilometer of air. So gamma rays are ones that are very concerning. That the ones that can kill you even if you don't ingest the material. So when we have an isotope that is unstable and is going to give off radiation, we refer to that as the parent isotope. So let's consider uranium-235. Uranium-235 is radioactive. If it's radioactive, that means it is unstable. It is not a stable configuration of the nucleus. In this case, it's too large. So it gives off an alpha particle. When it gives off an alpha particle, its mass changes. So it's a different mass, and it's lost 2 protons, so it becomes thorium. So the uranium-235 gives off an alpha particle, and it now has become presumably a more stable isotope, thorium-231. So the thing that it becomes through this process is called the daughter isotope. And generally speaking, but not always, the parent isotope is the more unstable one, and the daughter isotope is the more stable one. Now, strontium-90, it has too many neutrons. And since it has too many neutrons, it gives off beta particles. A beta particle is like an electron. It doesn't have much mass, right? None from an atomic perspective. So strontium-90 then becomes yttrium-90, which, again, is more stable. Now, I'm sure you've heard the term half-life. Maybe you played the game. It's pretty fun. Okay. I love that game. It's one of the only video games I've ever played. Anyway, the half-life of an isotope is something you're supposed to know on the test. And so here's the idea. So it is basically the amount of time it takes for half of the atoms in a sample to decay from parent isotope into daughter isotope. Now, there's no way of knowing when a particular atom is going to do this or nucleus is going to do this. But we can say there's the statistical probability. We're going to do a lab with this in class. And so for instance, let's just look at this here. Okay, so we're looking at cobalt 60. So let's just say that cobalt 60 has a half-life of 5 years. Right? It says 5.27. I'm just going to simplify. We're going to call it 5 years. Here's what that means. I start off with a pure sample that's 10 grams. I have 10 grams of pure 100% cobalt 60. It is 100% cobalt 60. After one half-life, that will be reduced to 50% as much. So instead of having 10 grams, I'll now have 5 grams. All right. And now that took 5 years to happen. So 5 years after acquiring this new sample, half of it will have decayed. I'll now have 50% as much. So if I started with 10, I now have 5. If I started with 100, I now have 50. If I started with 1,000, I now have 500. Whatever I start with, after one half-life, I have half as much. But I still have plenty of parent isotope left here, right? So what happens is, after another half-life, which in this case is 5 years, another half of it will be converted into daughter isotopes. So now half of 50 is 25. So after 2 half-lives, 1 and then 2, I'll have 25% left. So 25% of my initial amount of 10 grams is 2.5 grams. That's all that's left after 2 half-lives. In this case, 5 years. 5 years, it's been 10 years. After another half-life, half of this is going to decay. So half of 25 is 12.5. So after 3 half-lives, I've only got 12.5% left, which means I now have 1.25 grams of my original 10 grams that I started with. And this process just continues, okay? Well, another half-life would be half of 12.5, so that's 6.25. That's 6.25%. And in this case, that would be 0.625 grams. And you can see it becomes asymptotic until I'm down to an individual atom. But that's how radioactive decay half-lives work. The half-life is an amount of time in which it takes for half of the parent to decay into daughter isotope. Now, why is this important in what we're studying? Well, because isotopes that have short half-lives are very unstable. And what's going to happen is they're going to give off radiation at a very high rate. You don't want to be around them, but they're not going to last as long. Now, that's assuming that they don't decay into daughter isotopes that are also, we'll just assume the daughter isotope is stable, even though that's not usually the case. But isotopes with long half-lives are going to give off the radiation at a slower rate, but that means they're going to be radioactive for longer. So look at this graph I've got here. Okay, so I've got red isotope, I've got blue isotope. Okay, so the red isotope has a half-life of 10 years. Okay, so after 10 years, I only have half of the red one. But I still have like 70% of my blue one. Okay, after 20 years, now I only have 25% of my original red isotope, but I still have over 50% of the blue one. After three half-lives, I'm sorry, after 30 years rather, what I find is that the red isotope has been reduced to 12.5% of the starting amount, while I still have 50% of the blue. So the idea is it's decaying 3 times faster. However, it's only going to last 1/3 as long. I'll run out of this while I still have plenty of this one left. So that's the idea here. So short half-lives, you decay very quickly. In order to decay, you have to give off radiation. So if you think about it, half of the radiation that these 10 grams of red isotope are ever going to give off are given off in the first, in this case, 10 years. But it will take 30 years for this one to give off half of what it's going to give off. All right, let's keep going. Because half-life is this it's a clock, you can't vary it. There's nothing we can do to change the half-life of a nucleus, okay, of a particular isotope. So we can use it like a clock. So for instance, if I have 100 grams of the red isotope, and it starts off when it's pure, giving off 400 particles a second. Okay. Now, but some time goes by, and I sample it, and it's only giving off 100 particles. Well, how old is it? Well, now I know that the red one has a half-life of 10 years. Okay, we established that last time. It's 10 years, right? Well, how many half-lives must have gone by? Well, how many times did I divide 400 in half? If I divide 400 in half once, I get 200. And I've got less than that. Divide 200 in half, you have 100. Aha. So this has been divided in half twice. This is 25% of this. That means it's been 2 half-lives, and each half-life lasted 10 years. So the sample must be 20 years old. 2 half-lives, each of which lasted 10 years. 1 half-life, 2 half-lives. 20 years. So let's try this. Okay, so we can then use this to calculate, well, how radioactive is this particular sample going to be in a future time? Like we can say, well, we decide what a safe amount is, and we can tell you when that's going to be. You might hear like, this is going to be radioactive for 1,000 years. Here's how we know it, okay? So let's take the blue isotope. It has a half-life of 30 years. So when it's pure, it gives off 1,000 particles per second, okay? How much radiation is it going to give off 90 years from now? Well, the half-life is 30 years, so 90 years is the equivalent of 3 half-lives. So I take this 1,000 particles per second, the rate at which it's giving off radiation, and I divide it in half 3 times, once for each half-life. Half of 1,000, 1 half-life, gets me to 500. 2 half-lives gets me half of 500, that's 250. 3 half-lives is half of that, so half of 250, that's 125 particles per second. So after 3 half-lives, I'll have this much. I'll have 12.5% of the radiation being given off that was given off when it was pure. Compare that to the red one. The red one's only giving off 1.9 particles per second. How do I know that? Well, look, it has a half-life of 10 years. So how many half-lives has that been? Well, that's been 9 half-lives. So if I take 1,000 and divide it in half 9 times, I come up with 1.9. So that I think this gives you a very stark difference. Okay, so basically, whereas this is giving off 125 after 3 years, this one's after 30 years. Wait, I just got myself confused. 90 years. Okay, after 90 years, this is giving off 125, and this is only giving off 1.9. Okay, so this gets us to the biggest problem with nuclear power. The biggest problem with nuclear power is that fission products, fission fragments, whichever you want to call it. I call them fission fragments, but the APES test calls it fission products. These are the smaller nuclei that are formed when I split uranium or plutonium, whatever happened to split. They are super unstable. And that means you're going to have very short half-lives and give off radiation at a very alarming rate. And here's why. It takes a lot of neutrons to bond a big atom like element 92 uranium together. It does not take nearly that many to bond together rubidium or cesium. So what happens though is when I split this, 3 of the neutrons are going to go off. Remember, because it's fizzled, they're going to go off and split other nuclei, presumably. But I still have way more neutrons than I need for a cesium atom and way too many neutrons than I need for a rubidium atom. So they're going to give off radiation at a crazy rate. So look at this. The half-life of uranium-235 is 700 million years. It's radioactive. It's not that radioactive. This rubidium that gets formed, 5 seconds. The cesium, 68 seconds. And then it's going to decay into some other isotope, but it's still going to have too many neutrons, and so that's going to be radioactive. So it turns out that the fission fragments are insanely radioactive, but they have short half-lives, so they don't last that long. Although the things they decay into last longer and longer. So consider this. It is perfectly safe for you to hold a uranium-235 fuel pellet in your hand. In fact, you could take a fuel rod that's never been put into a plant, just put these things here into a titanium fuel rod. You can sleep with it at night like a instead of a teddy bear. You say, "Oh, I love my little fuel rod. It keeps me warm at night." Although it wouldn't really. Point is, you're not going to get exposed to enough radiation to cause you any harm, even if you sleep with it your whole life. The thing is, though, once you put that in a reactor and start splitting those nuclei, it's a whole different story. And by the way, there have been people who have accidentally swallowed these things and nothing happened. They just waited for them to poop them out and they were just fine. Okay. But when I put in a fuel rod into a reactor and I start splitting those nuclei, they become so radioactive that when I pull them out, you can't even be near them. You had to pull them out robotically. You can't even be near them. You had to store them into these deep pools of water, and the radiation they're giving off is so intense it causes basically shock waves of light in the water from the gamma rays that cause the water to give off this weird bluish glow. It's so weird, okay? And they just had to let them settle down and cool off for a while. It's not really so much cooling off so much as it is going through a number of half-lives. These are very rapid half-lives, giving off radiation really, really, really fast. And eventually, after let's say a few years, let's say like maybe 3 years, you can take them out of there, and they have decayed into a stable enough form, although they're still very radioactive. You put them into these storage containers that are about this big compared to a person. Now, ideally, what would you do with them? These are metal. These are metals, right? These are uranium. These are mostly metals. And I've got them inside titanium tubes, which they can't get out of, and I put that inside of a lead container, which it can't get out of, inside of basically there's multiple layers of containment is my point. It's not going to get out into the environment and get ingested by people. But then even better, we can put it in some sort of deep storage. So what I can do is I can put it inside some sort of open geological formation, or I could go and get it out if I wanted it in the future. I could put it in one where geological forces will kind of seal it in and keep it safe, right? But unfortunately, what's happening in the United States is we built this place called Yucca Mountain. So we basically built this storage facility we could put our nuclear waste in. But to get it there, you had to drive across state lines. And this was in the state of, I think it's Nevada. And they're like, you ain't put in our state. And so as it is right now, all the nuclear waste in America is stored on site, which is not what we want. It's distributed. And that's really not a very safe way of doing things. And so we're still waiting for a solution. But in a way, it's good that we didn't do this. It's good that we didn't put them in a sealed one. And here's why. Turns out there's value in these things. Okay, we could potentially get some energy back out of it. Now, one of the things you're asked to know on the APES test is the distribution of these resources. So it's worth knowing that whereas Australia had almost no coal to speak of, no oil to speak of, man, they're kings of uranium. 30% of the world's uranium is in Australia. Lucky them, and lucky that we like them, right? But then some of it's in Kazakhstan and Russia too. They have a lot of it, and so does Niger. USA has quite a bit as well, as does Brazil and Canada, right? So we see. It's worth noting that Australia, Kazakhstan, Russia, Canada, these are kind of the big players in terms of the world's uranium reserves. Now, if we were to just keep using uranium the way we do it now, the way we've done it since the 1950s, 60s, okay, it's not going to last forever. It's a non-renewable resource. And the APES test will tell you, if they ask you, you say non-renewable. I care about more than the APES test. And I really want you to understand this. Uranium is a path forward for humanity. It could save us from a lot of things, namely global warming and running out of energy and having our civilization collapse around us. If we just keep doing it the way we're doing it, we'll go through your world's uranium reserves. I mean, if we started scaling up and using it for everything in about 100 years, okay? I mean, if we use it at our current rate, it lasts a lot longer. But if we just said we're going to use it for everything, it lasts about 100 years, right? But it turns out that these aren't the only places where you can get uranium. Recent technology using nanotechnology allows us to extract it from seawater. And there's a lot of it in seawater. And it's constantly seeping into the seawater from rivers. And it turns out this technology is advancing very rapidly, and it seems scalable. And so in the near future, we would be able to extract uranium from the seawater at a rate that would make it essentially a renewable resource. Like the rate of our extraction from the ocean would be less than the rate at which it comes into the ocean, and it would match our energy needs. If based on this, we could have nuclear power forever. And remember, it doesn't make the skies dirty, right? We have to watch out for nuclear meltdowns, right, and contamination, but it's energy that will last us essentially forever. But wait, there's something else, and this is something that is here now and growing. So extracting uranium from seawater is being developed. The technology is being proven, and it seems like it's a go, although it isn't fully operational yet. But this is. So we don't have to use standard nuclear reactors. We could use a thing called fast neutron reactors. So a fast neutron reactor is, remember, instead of trying to slow it down with water or graphite, instead of using a moderator to try to increase the likelihood of splitting uranium-235, you let the neutrons go fast, and when that happens, you end up converting uranium-238, which is not usable, right? It's not fissile, but you end up converting into plutonium-239. And then what happens then is that the thing does split, and so basically you can turn all this uranium-238. Remember, like 997 out of every 1,000 atoms of uranium on the planet are uranium-238, and right now they don't do us any good. In this process, they do us good. And not only that, okay, so what happens is not only does this allow us to extend our supplies by a factor of 60, so instead of running out in 100 years, we'd run out in 6,000 years, even if we never figured out how to extract uranium from water. But then there's this. It also causes the splitting of these very large actinides, so things that are bigger than plutonium, things like americium and curium, things that are the real problems with nuclear waste, the things that are really hazardous. It splits those, and it causes the whole problem of nuclear waste disposal to be considerably less problematic. So this is a wonderful technology. It's proven. It's existed. Right? There's a number of these operational facilities in use today. Just real quick. So a neutron hits uranium-238. It absorbs it. It becomes uranium-239, which gives off a beta particle, and that becomes plutonium-239. So the next neutron that hits it, it splits and releases its energy. Cool, huh? Now, so fast neutrons, they can split these heavy isotopes and make the nuclear waste much less of a problem, because it's only now going to be dangerously radioactive for a few decades rather instead of hundreds or thousands of years. And there's a lot of these in operation right now, and there's more coming online. So this is probably going to be the way nuclear reactors operate in the future. All right, that took a little bit longer than I thought because I get all excited about it. Sorry about that.